Hello and welcome everybody. Thank you for joining us today. We have very good crowds from all over the world as usual. So I thank you for taking the time to be here today. So about Dr. Shihab, Dr. Shihab is a graduate from structural engineering. He received his PhD from University of Sherbrooke in Quebec, Canada, just a couple of years ago in 2021. Before that, of course, he did his bachelor's degree and master's degree in civil engineering. He specialized in structures like infrastructure projects or elements. And he did that in Egypt back in 2013 and 16. These degrees provided him with a comprehensive understanding of the concept of civil and structural engineering and paved the way for his specializing in structural engineering eventually in the University of Sherbrooke. His research at the University of Sherbrooke includes the use of FRP polymers in reinforced concrete structures. One significant area of focus for Dr. Shihab, is investigating the mechanical and properties and the performance of GFRP bars in concrete structures. I guess he's the right person to ask questions about that if you have any. He also delved into the behavior of FRP reinforced members under various loading conditions such as tension, compression, and flexural. In his research, Dr. Shihab also focused on optimizing the design and detailing of FRP reinforced concrete elements. This involves considering factors such as material compatibility, bond behavior, and interaction between FRP reinforcement and concrete. So, as I said, he's the right person to listen to in this subject. I'll give the mic to him. Dr. Shihab, the mic is yours. Enjoy, everybody. Hopefully the presentation will add to your information.
Yes, thank you so much, Rick, for the brief introduction. Good afternoon, everyone. Today I'll talk about flexural behavior and the serviceability performance of concrete members and FRP bars. So through this presentation, I'll give a brief overview about FRP bars, applications of FRP bars, cracking and ultimate moment equations, also crack control and the deflection equations, and lastly, example of the flexural strength and the serviceability performance of concrete members reinforced with FRP bars. First, our products are mostly designed in Canada and manufactured in China. We work with national and international engineering companies. We work with them through the design process and help them with the FRP design standards. Actually, we focus on parking facilities, water treatment plants, and retaining wall as well. So our focus is mainly on the glass fiber bars and the carbon scrap applications. As mentioned, there is 2 points that should be noted. The first one, the GFRP bars have lower strength compared to the other 2 types of GFRP bars, while the second one is the strength of all of GFRP bars, of all FRP bars, GFRP bars, armored and the carbon FRP bars is higher than the steel bars. So we can produce different types of FRP products depending on the project requirements. Some of the FRP bars where we produced are first straight bars, spiral, stirrups for transverse reinforcement, bent bars, and lastly glass FRP shear connectors. Some of the advantage of static GFRP bars over the steel bars are: the first one, it's a longer surface life because of its corrosion resistance, therefore improve the durability in the harsh environmental conditions. The FRP bars have better resistance against corrosion compared to steel bars. The tensile strength of FRP bars is 2 to 3 times more than that of the steel bars. And lastly, however, it's more tensile strength. FRP bars are lighter due to the low density compared to steel bars. So the FRP bars started to use in the periodic slab in North America since 1999. The GFRP bars were preferred because of its low cost compared to the other available FRP bars. Here are some of the examples of the periodic slab constructed with GFRP bars. Now, by moving coming to the design philosophy of the FRP reinforced concrete structures, first we need to understand how it's different from the steel reinforced concrete structures. Actually, there is three different design philosophy. The first one, balanced section, second, under reinforced section, and the last one, over reinforced section. The steel reinforced concrete structure follows the under reinforced section where the failure occurred due to steel failure, which can provide ductility to the structure before failure. By following the under reinforced section for FRP bars, actually the FRP reinforced concrete structures will have rupture of FRP before the concrete crushing, which is it's not suitable for the structures as the structure may fail in brittle manner. Therefore, to avoid these situations, the over-reinforced concrete, the over-reinforced section is considered for the FRP reinforced concrete structures. Therefore, the concrete crushing occurs before the FRP failure. So let's move to the cracking and ultimate moment equations. As can be seen, the cracking moment depends on the concrete tensile strength, where lambda is the concrete density reduction factor. For lightweight concrete, of course, which is equal to 0.75 to 0.85 as recommended by ACI 318/2019, based on the percentage of the aggregate in the mixed design. On the other hand, the ultimate moment can be calculated by considering the force equilibrium as strain compatibility. Now, let's move to the crack control. This slide provides the theoretical approaches used for calculating the crack width predictions for the FRP reinforced concrete members. So according CSA S6 2019 specifies a direct procedure to control crack width where KB is the bond dependent coefficient, which calculates the bond between the FRP bars and the surrounding concrete. On the other hand, ACI 440 2015 guideline specified an indirect procedure to control crack widths with a maximum bar spacing. Actually, the KB value shall be determined experimentally, but when the experimental data is not available, S6 2019 recommends a KB equal to 0.8 for sand-coated FRP bars and 1 for deformed FRP bars. On the other hand, ACI 440 2015 guideline suggested a conservative value of 1.4 for all types of FRP bars. So a similar equation is currently being considered for the new ACI 440 code by replacing the crack width W in the ACI 440 2015 equation with 0.71 millimeter. So recently, the ACI 440 committee approved a single conservative value of 1.2 for all types of GFRP bars based on a study conducted by Bemokran et al. 2023. Lastly, Ashto 2018 recommended the same equation as the equation in ACI 440 with introducing the term CB instead of the traditional KB. Actually, Ashto specifies a value of 0.83 for CB, while as CB equal to 1 divided by KB, then the KB equal to 1.2 for all type of FRP bars. Now turning to deflection, this slide provides an overview for deflection equations for the FRP reinforced concrete members. This equation can be used to estimate the deflection for a simply supported member where IE is the effective moment of inertia. According to ACI 440, the IE can be estimating from this equation. On the other hand, CSA S806 2012 re-uploaded 2021 recommended this equation to estimate the deflection by assuming a fully cracked section without any contribution of tensile stiffness in cracked zone. So let's move to the examples. As we can see here, we need to design a rectangular beam of width of 300 millimeter to resist the surface load moment due to dead load equal to 76 kilonewton meter and due to live load equal to 47 kilonewton meter. And we assume the beam is interior in the building, enters the building. So the given is the compressive strength of concrete is 28 megapascal. The ultimate tensile strength for FRP bars 440 megapascal, and the modulus of elasticity of the FRP is 45 gigapascal. So first, starting point for design of the reinforced concrete members for unknown dimensions is to assume the reinforcement ratio. So as we know, as we mentioned earlier, we need to design the section to fail in compression control. Therefore, we will assume the reinforcement ratio higher than 1.4 the balanced reinforcement ratio. In our example, we will assume reinforcement ratio equal to 1.5 balanced reinforcement ratio. Therefore, we need to calculate the balanced reinforcement ratio first. We can calculate it using this equation. We will calculate it based on the ACI 440. Therefore, we will use the epsilon CU equal to 0.003. If we will calculate it using S806, we will use 0.0035. Okay. So from this equation, we can calculate the balanced reinforcement ratio and multiply with 1.5 to have the reinforcement ratio, the assumed reinforcement ratio. And as mentioned, because reinforcement ratio higher than 1.4, the balanced reinforcement ratio, the section is compression controlled. The second step, we need to compute the BG square required. So to do that, we need first to determine the required design moment strength from this equation based on the load combination, the M ultimate equal to 1.2 moment from dead load plus 1.6 moment from dead live load. And it will be equal to 166.4 kilonewton meter. So we can calculate the stress in tensile reinforcement at ultimate condition for the assumed reinforcement ratio using this equation, which can be found in ACI 440. Actually, all these equations are based on the strain compatibility as mentioned in the equation of the cracking and ultimate moment equations. Therefore, the stress will be equal to 349 megapascal. Right now, by applying all the parameters in this equation, we can find the BD square equal to this number. And therefore, we can calculate the D, the effective depth of the section, which will be equal to 414 millimeter. The last step in this example is to determine the required reinforcement, steel bars, and determine depths. So actually, to calculate the area, the area of FRP required, we will use this equation. It's the reinforcement ratio of FRP bar multiplied by B multiplied by D, which we will have area of FRP bars equal to 2011 millimeter square. So we have to select the bar size. In this example, we will select size number 8 by divided the total area, divided the total area by the area of the one bar. We will have 4 bars number 8. So right now we have to check the moment capacity of the section. So first assume actually this example didn't include the design of shear reinforcement. So we assume that we have reinforcement stirrups number 13. So the total depth of the sections that we have, it will be the effective depth 414 plus the concrete cover 38 plus the diameter of the stirrup 12.7, and lastly the diameter of the FRP bars divided by 2. So we will have 477 millimeter. So we will select first the section to be 300 multiply 500 millimeter for the beam. To check, we need to calculate the actual depth, the effective depth from this equation, which will be 437 millimeter. After that, calculate the actual reinforcement ratio based on the actual area of FRP bars and the actual cross section of beams that we have. And check if the reinforcement ratio is higher than the balanced 1.4, the balanced reinforcement ratio or not, because as we mentioned earlier, the ACI 440 recommended to have the reinforcement ratio higher than or equal to 1.4 balanced reinforcement ratio. After that, we can calculate the stress. Therefore, we will calculate the moment capacity of the section that we have based on the actual reinforcement ratio, the width, and the actual depth. So the actual moment capacity will be 182 kilonewton meter, which is higher than 166 kilonewton meter. Therefore, we are safe. The second example that we have right now, we have a concrete beam reinforced with FRP bars, as shown in this figure. This beam has a span of 3,300 millimeter over assembly supported, and it has considering a surface moment equal to 30 kilonewton meter, and we need to calculate the crack width and the deflection for this beam. The givens that we have right now for concrete, the compressive strength is equal to 32 megapascal, methods of elasticity for concrete 27 gigapascal. For fiber glass reinforcement, the tensile strength it's 1,150 megapascal. Modulus of elasticity for FRP equal to 52.5 gigapascal. The diameter and area equal to 20 millimeter and 284 millimeter square respectively. So first, to calculate the crack width, so we will use this equation W crack to FRP divided by modulus of elasticity of FRP multiply these parameters. So we need first to calculate these parameters. We need to calculate the effect. As we have 2 layers of reinforcement, we need to calculate the average, the effective depth. To do that, we need to calculate first the effective depth for the first layer. the effective depth for the second layer and take the average between them. After that, we have to calculate the reinforcement ratio from based on the effective depth that we have. Calculate the stress of FRP bars. Assume the KB equal to 1.2 as we don't calculate it experimentally or determine it experimentally. We have to use the number in the standard. So we will use KB equal to 1.2. After that, we will use these parameters to calculate the crack width, which will be equal to 0.49 millimeter, which is lower than 0.5 millimeter. Therefore, it's safe. So right now we have to calculate the deflection. As mentioned, we need to calculate the crack width and the deflection for this example. So to calculate the deflection, we have to use this equation. But we need first to calculate the parameters that are the terms of this equation. So first we need to calculate the neutral axis of the section. So actually we can calculate the neutral axis of the section by this equation, or use simplified equation by dividing the height is the depth of the section by 2. The same thing for the cross section, the gross moment of inertia. We can use BT cubic divided by 12, and after that we can calculate the tensile strength of concrete by this equation 0.6 f prime root of f prime c. Therefore, we can calculate the effective the cracking moment of inertia, that we will use it to calculate the effective moment of inertia from the equations that we mentioned to calculate the deflection over there in the equation, and therefore we will use all these terms to calculate the deflection for the sections that we have and check it with the allowable if it's okay or not. In our equation, in our example, the deflections that we have was 16 millimeter, and the allowable deflections that we have, it's around 9 millimeter, which the actual deflection is higher than the allowable deflection, and therefore this example is not. Thank you so much.
Thank you, Dr. Shihab, for the presentation and for the information you provided.